56 million years ago, something pumped more carbon into Earth's atmosphere than all of human industry combined. It happened quickly. It left behind a chemical signature in the rock, a signature scientists have spent the last 30 years trying to understand. And that signature points overwhelmingly to one source above all others: burned biological matter. The same fingerprint as fossil fuels, the same fingerprint as industrial emissions. And even today, no natural explanation fully accounts for the sheer volume of that carbon. In 2018, two NASA-affiliated scientists published a formal paper asking a question that no major institution had been willing to ask openly before. If an industrial civilization had existed on Earth tens of millions of years before us, would we even know? They ran the numbers. They modeled what survives across geological time, what degrades, what vanishes. Their conclusion was brutal. We would not know. The evidence would look exactly like a natural event. It would be assigned a name. It would be assigned a date. And the question of what caused it would remain officially unresolved. Then they looked at the geological record, and they found exactly that. An event with a name, a date, and an open question that 30 years of research has still not closed. This is not mythology. This is not fantasy. This is the data. Let us begin. The event is called the Paleocene-Eocene Thermal Maximum, abbreviated as the PTM. It sits in the geological record at approximately 56 million years before the present, embedded in layers of ocean sediment and carbonate rock sampled from every major ocean basin on Earth. The basic facts of the event are not disputed. They are among the most thoroughly documented and extensively studied phenomena in the history of paleoclimatology. Between 3 and 7 trillion tons of carbon entered the atmosphere in a geologically brief interval, roughly a few thousand years. Global temperatures rose by 5 to 8 degrees Celsius. The deep ocean acidified. Roughly 1/3 of all species living on the ocean floor went extinct. The planet required approximately 200,000 years to recover. 200,000 years. That is longer than modern humans have existed as a species. Whatever caused the PTM pushed Earth's climate so far beyond equilibrium that the system needed a span of time longer than the entire history of Homo sapiens just to stabilize again. To understand why the PTM is such a problem, you only need to understand one thing about carbon. Just one. Everything else follows from it. Carbon exists in two stable forms, two isotopes that differ by the weight of a single neutron. Scientists call them carbon-12 and carbon-13. Carbon-12 is the lighter form. Carbon-13 is the heavier one. Both occur naturally wherever carbon exists, but the ratio between them is not uniform everywhere. And that difference is the key to reading this planet's past. Living organisms prefer the lighter isotope. Every plant, every animal, every bacterium on Earth preferentially incorporates carbon-12 into its biological processes. That means anything derived from once living material, wood, peat, coal, oil, natural gas, carries a distinctive isotopic signature. It is enriched in the lighter isotope. Scientists call this a negative carbon isotope excursion, when that biologically light carbon floods into the atmosphere and gets recorded in the geological record. Volcanic carbon, by contrast, comes from deep within the Earth. It has not passed through biology. It carries a heavier isotopic signature, closer to the natural background ratio of the Earth's interior. These two fingerprints are as distinguishable as two different blood types. You cannot mistake one for the other. The carbon that drove the PTM has the biological fingerprint, light carbon, organic source. Every measurement taken across 30 years of research, from ocean sediment cores drilled in the Atlantic, the Pacific, the Indian Ocean, and the Southern Ocean, confirms this. The carbon isotope excursion at the onset of the PTM is one of the clearest and most consistently replicated signals in the entire geological record. It is not ambiguous. It is not debatable. The carbon that triggered one of the most severe climate disruptions of the last 66 million years has the chemical signature of burned or decomposed biological material. Not volcanic rock, not a deep earth process. Something that was once alive. Now here is the question textbooks handle delicately but never quite answer. What biological source on Earth was large enough to release 3 to 7 trillion tons of isotopically light carbon into the atmosphere in only a few thousand years? The standard explanations usually involve three candidates. The first is volcanic activity. Around the time of the PTM, a large igneous province was erupting in what is now the North Atlantic, associated with the opening of the Atlantic Ocean between Norway and Greenland. These eruptions were massive and prolonged, releasing substantial quantities of carbon dioxide over tens of thousands of years. But volcanic carbon carries the heavier isotopic signature. It does not match the light carbon fingerprint of the PTM. Volcanic activity almost certainly contributed to the event, most likely by warming the climate enough to trigger secondary carbon releases. But it cannot be the primary source of the isotopically light carbon that defines the event. The second candidate is methane hydrate. Vast amounts of methane are stored in frozen deposits on the ocean floor, trapped inside crystalline structures of water ice under high pressure and low temperature. Methane is a powerful greenhouse gas, and its carbon is biologically derived, which means it carries the light isotopic fingerprint. If the ocean warmed enough, these deposits could destabilize, releasing enormous amounts of methane into the ocean and atmosphere over a geologically short interval. This mechanism fits the isotopic signature, it fits the speed, and it is almost certainly part of the answer. But when researchers model the total volume of methane that could have been released from known and estimated hydrate reservoirs at the time, they come up short. The models do not generate enough methane to explain the full 3 to 7 trillion tons of carbon recorded in the sediment. The third candidate is the thermal decomposition of organic-rich sediments. When volcanic intrusions penetrate layers of carbon-rich rock, the heat can cook the organic material and release methane and carbon dioxide. This mechanism produces isotopically light carbon, and was likely active in the North Atlantic during the volcanic activity associated with the PTM. It contributes significantly to the total carbon budget, but like methane hydrates, it still does not close the gap entirely. When you add up every known natural source, volcanic outgassing, methane hydrate destabilization, thermal decomposition of organic sediments, the total still falls short. The volume of isotopically light carbon recorded in the geological record exceeds what the combined natural mechanisms can reliably produce. This shortfall has been noted in the published literature for decades. It is not hidden. It is not controversial. It is a recognized gap in the explanation of one of the most studied climate events in Earth's history. Scientists describe it in technical language. They refer to additional carbon sources that have not yet been fully identified. They use careful phrasing. They note that the models are sensitive to assumptions about initial conditions and feedback mechanisms. But the gap remains. 30 years of research, thousands of published papers, the most intensively studied rapid carbon event in the geological record, and the numbers still do not balance. This is where the story changes direction, because in 2018, a paper appeared that reframed the entire question. Gavin Schmidt, director of NASA's Goddard Institute for Space Studies, and Adam Frank, a professor of astrophysics at the University of Rochester, published a formal study in the International Journal of Astrobiology. The paper was titled The Silurian Hypothesis. Would it be possible to detect an industrial civilization in the geological record? The name was borrowed from a 1970 episode of Doctor Who, a deliberate choice meant to acknowledge the speculative nature of the question, while treating the physics with complete seriousness. Schmidt and Frank did not claim a previous civilization existed. What they did was ask a precise and technically rigorous question. If a civilization comparable to ours had existed on Earth tens of millions of years ago, what evidence would survive in the geological record? And would we even be able to distinguish that evidence from a natural event? They modeled the problem systematically. Buildings, concrete, steel, none of it survives more than a few tens of thousands of years. Geological forces, erosion, compression, chemical weathering, the relentless recycling of Earth's surface through plate tectonics. These processes erase manufactured structures entirely within a time frame that is less than a rounding error on the geological scale. Plastics, which we think of as nearly indestructible, degrade within a few 100,000 years. Nuclear waste leaves isotopic traces, but those traces fade and blend into natural background variation over millions of years. What survives 50 million years of geological processing is chemistry. Isotope ratios locked into carbonate rock, trace metal concentrations in sediment layers. A carbon signal with a specific fingerprint recorded in the chemistry of the ocean floor, and preserved indefinitely. That is it. No city outlines, no road foundations, no garbage layers, recognizable as garbage. Just numbers in a thin band of ancient rock that require interpretation to mean anything at all. Their conclusion was exact and deeply uncomfortable. A civilization comparable to ours could have existed, expanded, burned through its planet's stored carbon, and collapsed, and the geological record would not identify it as a civilization. It would identify it as a geochemical event. It would be given a name, and a date, and a place in the literature. Researchers would study it extensively. They would note anomalies in the data, and the question of what caused it would remain officially open. Now read that conclusion again, and then look at the PETM. A carbon event with a biological fingerprint. A volume that exceeds the known natural sources. A rate of release comparable to large-scale industrial output. An open gap in the explanation that 3 decades of research has not closed. Sitting in rock that is 56 million years old, at a time when this planet had already been habitable for complex life for hundreds of millions of years. Schmidt and Frank were not writing specifically about the PETM, but what they described is an exact match for what the PETM data shows. 2 independent lines of published, peer-reviewed science. One says we would not be able to tell the difference between the footprint of a vanished civilization and a natural geochemical event. The other shows us an event whose footprint contains a gap no natural explanation has fully closed. That connection has been sitting in plain sight since 2018, and almost nobody in mainstream science has been willing to put those 2 observations in the same sentence. Something left that fingerprint in the rock 56 million years ago. We know what the fingerprint looks like. We do not know what produced it. And we now have a formal scientific framework demonstrating that we may never be able to know with certainty either way. That is not the end of the question. That is the beginning of it. And in the chapters that follow, we will trace every thread of evidence connecting the PETM to the deepest mysteries buried in the geological record, in the stone monuments of forgotten builders, and in the chemistry of the atmosphere we are breathing right now. Before we move into the next chapter, if you are kind enough, a gentle like and a tap on subscribe to Skyline Trek would mean the world to me. It is a small gesture, but I hold it with real gratitude, because every bit of your support keeps this tiny universe alive. Here is a thought experiment. Take everything humanity has ever built. Every city on every continent. Every bridge. Every dam. Every skyscraper. Every road. Every power plant. Every mine. Every landfill. Every factory. Every ship rusting in a harbor. Every satellite in orbit. Every plastic bottle floating in every ocean. All of it. The accumulated physical output of 8 billion people across 2 centuries of industrial civilization, stacked on top of 300,000 years of human existence. Now leave it alone. Walk away. Let physics do what physics does. Come back in 50 million years and see what remains. The answer is almost nothing, and the precise way in which it becomes almost nothing is the key to understanding why the question raised by Schmidt and Frank cuts much deeper than most people realize. Start with the structures. A modern skyscraper built from steel and reinforced concrete begins to deteriorate the moment maintenance stops. Within decades, water infiltration cracks the concrete and corrodes the rebar inside it. Within centuries, structural integrity fails and the building collapses under its own weight. Within a few thousand years, the rubble is buried beneath sediment, overgrown by vegetation, weathered by rain and wind and frost. Within tens of thousands of years, the steel has oxidized completely. The concrete has chemically decomposed. What remains is a lens of chemically unusual soil, enriched in certain elements, calcium, iron, aluminium, but with no geometry, no shape, no structure that would tell a future geologist that something had once been intentionally built there. It looks like a natural deposit. It gets catalogued as a natural deposit. A city the size of New York becomes a thin smear of anomalous chemistry in one compressed sediment layer. No outlines, no foundations, no indication that intelligence had anything to do with it. Now consider the materials we think of as permanent. Plastics. We produce more than 400 million tons of them every year. We worry about plastic pollution as though it will mark the Earth forever. It will not. Ultraviolet radiation breaks the polymer chains. Microbial activity accelerates the decay. Within a few 100,000 years, the plastics are gone. chemically absorbed into the sediment, leaving behind trace concentrations of unusual carbon compounds that a geochemist with the right instruments might detect, but would never identify as packaging or bottles or bags. They would be catalogued as an organic carbon anomaly, nothing more. Metals fare slightly better in terms of persistence, but no better in terms of recognizability. Copper, lead, zinc, rare earth elements, concentrated by mining and industrial processing, can persist as anomalous concentrations in sediment for millions of years, but without context, without surviving structures or artifacts to connect them to, they look like natural mineral deposits. The Earth naturally concentrates metals through volcanic activity, hydrothermal processes, and weathering. A future geologist would need an extremely specific reason to suspect that a particular enrichment of rare earth elements in a 50-million-year-old sediment layer was caused by a factory rather than a volcanic vent, and chemistry alone would not provide that reason. Nuclear material is the longest-lasting identifiable trace. Some radioactive isotopes produced by nuclear reactors and weapons have half-lives measured in millions of years. Plutonium-239, for example, has a half-life of roughly 24,000 years. After 50 million years, even the longest-lived fission products would have decayed to levels that are extremely difficult to distinguish from natural background radiation. A few anomalous isotope ratios at certain locations might survive, but interpreting them as evidence of technological activity rather than, say, a natural nuclear fission reactor, like the ones that existed at Oklo in Gabon roughly 2 billion years ago, would require a framework no geologist would have reason to apply. So what actually survives 50 million years in a form that remains unambiguously readable? One thing, the carbon signal. The isotopic composition of carbon locked into carbonate rock and ocean sediment. Light carbon enriched in the carbon-12 isotope, deposited globally and rapidly, in volumes corresponding to the massive combustion of ancient organic material. That signal is durable. It is global. It is locked into the chemistry of the ocean floor by organisms that build their shells from dissolved carbon in seawater. When those organisms die and their shells accumulate on the seabed, the isotopic signature of the carbon they incorporated is preserved in the resulting limestone. 50 million years later, a researcher drilling into that limestone and running the sample through a mass spectrometer will find the signal exactly where it was deposited, exactly as strong as when it was first recorded. The carbon signal is the one message geological time cannot erase. Now here is the part you need to sit with for a moment. We are producing that signal right now. 150 years of industrial activity, primarily the combustion of coal, oil, and natural gas, has released roughly 500 billion tons of isotopically light carbon into the atmosphere. That carbon is being absorbed by the oceans. It is being incorporated into the shells of marine organisms. It is being deposited on the seabed in sediment that will one day become rock. The isotopic signature of our industrial civilization is being written into the geological record at this very moment. In 50 million years, it will still be there. A thin layer of light carbon, anomalous, rapid, biological in origin, with a volume that future researchers may or may not be able to fully account for, using natural mechanisms available in their models. We are creating our own PTM. We are writing the same entry into the same record, with instruments precise enough to watch ourselves do it in real time. And the most unsettling realization is not that we are doing it. It is that someone or something may have done it before. What happened after the Silurian hypothesis was published? The answer to that question is almost as revealing as the paper itself. Almost nothing. The paper appeared in the International Journal of Astrobiology in 2018. It was covered by mainstream science publications. It generated brief public interest, and then the field moved on. No major follow-up studies. No funded research programs. No teams assembled to rigorously test the hypothesis against the specific anomalies of the PTM or any other geological event. 7 years of silence from the very institutions best positioned to pursue the question. That silence is worth examining. In the normal process of science, when a credentialed researcher publishes a novel hypothesis in a peer-reviewed journal, the community responds. Other scientists test it. They try to confirm it or break it. They run their own models. They look for predictions the hypothesis makes, and test whether those predictions match reality. That adversarial process is how science corrects itself. It is how good ideas survive and bad ones are discarded. The absence of that process is not neutral. It tells you something. But what it tells you is not that the hypothesis is wrong. If the hypothesis were obviously wrong, it would have been easy and professionally rewarding to write a rebuttal demonstrating its flaws. No such rebuttal has been published. What the silence tells you is that the question is professionally dangerous. The incentive structure of academic science is asymmetric. If you pursue the Silurian hypothesis and find evidence supporting it, the discovery would be extraordinary, but the professional risk is enormous. If you are wrong, your credibility is damaged permanently. You become the scientist who chased ancient industrial civilizations in the geological record. No amount of methodological rigor protects you once that label attaches to your name. If you stay quiet, nothing happens to you. You continue publishing within the accepted framework. You continue receiving funding. You continue advancing. The cost of asking the question is borne entirely by the person who asks it. The cost of not asking it is distributed invisibly across the field. Nobody is punished for leaving the gap open. Only the person who tries to close it takes a risk. This creates a blind spot that is structural, not conspiratorial. No one decided in some dark room to suppress the Silurian hypothesis. What happened is simpler and more human. Everyone individually calculated the professional cost and benefit of engaging with it, and everyone individually concluded that the cost was too high and the benefit too uncertain. The result is a collective silence that looks like consensus, but is actually the absence of investigation. The question was not refuted, it was abandoned. And there is a difference between a question that has been tested and found wanting, and a question that has never been tested because no one was willing to go first. Here is the number that makes that abandonment intellectually indefensible. Earth has been habitable for complex multicellular life for roughly 600 million years. The Cambrian explosion, the sudden appearance of most major animal phyla in the fossil record, occurred approximately 540 million years ago. Since then, the planet has supported an unbroken chain of increasingly complex biological diversity. Modern humans have existed for roughly 300,000 years. Our industrial civilization has existed for about 200 years. That means our entire industrial presence on this planet represents roughly 1/3 millionth of the window during which complex life has existed. 1/3 millionth. Now ask the question that no mainstream institution has formally calculated. What is the probability that in 600 million years of complex biology on a planet chemically favorable to life, with oceans rich in organic chemistry, and an atmosphere capable of supporting metabolisms of extraordinary diversity, we are the first and only species to develop the capacity to alter the atmosphere at an industrial scale? Not the first to build radio telescopes, not the first to write poetry, the first to burn stored organic carbon at a rate sufficient to leave a detectable isotopic signal in the geological record. That is a much lower bar than intelligence. It only requires the biological capacity to extract and combust stored energy at scale. And in 600 million years, across millions of species, through mass extinction events that repeatedly wiped the ecological slate clean and opened new evolutionary pathways, we are expected to believe it happened exactly once. The honest answer is that we do not know. We cannot prove something was here before us, but we also cannot prove that nothing was. And those two positions are not symmetrical. One is comfortable. The other requires us to rethink our place in the history of this planet. We have collectively chosen the comfortable one, and we have done so not because the evidence supports it, but because the absence of evidence in a record we now know cannot preserve the relevant evidence has been treated as if it settles the question. It does not. The record is not clean. The record is blind, and what we cannot see is not the same thing as what did not exist. The PTM fingerprint sits in the rock. The gap in the explanation sits in the literature. The framework that connects them sits in a peer-reviewed journal with only a handful of citations and 7 years of silence. 3 independent facts, 1 deeply uncomfortable intersection, and a question still waiting for someone brave enough to pursue it with the resources and rigor it deserves. In the next chapter, we leave the chemistry of ancient carbon behind and move into the physical evidence layer of a much more recent catastrophe, one that left its marks not only in isotope ratios and sediment cores, but in nanodiamonds scattered across 4 continents, in a crater hidden beneath a mile of Greenland ice, and in the sudden disappearance of an entire culture from the archaeological record. Something happened 12,800 years ago, and the evidence for what it was is far more tangible than a chemical signature locked in ancient rock. 12,800 years ago, the world was warming. The last ice age was loosening its grip. Glaciers that had covered large parts of North America and Northern Europe for tens of thousands of years were retreating. Sea levels were rising. Forests were reclaiming land that had long been buried under miles of ice. The megafauna of the Pleistocene, mammoths, mastodons, giant ground sloths, saber-toothed cats, still roamed a continent, becoming more hospitable with every passing century. And
the
then,
Orion Nebula,
in a window so
stellar
narrow,
nursery
geology cannot distinguish it from a
1,344
single
light
moment.
years away.
Everything reversed.
Data streams in,
Temperatures
revealing
plunged.
stellar
The
evolution
warming
in
stopped.
real time.
The glaciers advanced again. Ecosystems that had been recovering for millennia collapsed. The largest animals on 4 continents vanished from the fossil record. An entire human culture disappeared so completely that for decades archaeologists did not know where it had gone. The event is called the Younger Dryas, named after a small Arctic flower that reappeared in European pollen records during the cold snap, a botanical signal of a world that had suddenly become colder by perhaps 1,000 years of climate. The Younger Dryas lasted roughly 1,200 years. It was abrupt in and abrupt out, and the question of what caused it has been fought over in academic journals for 4 decades, with an intensity that suggests the answer matters far beyond paleoclimatology. The standard explanation is elegant and well supported. A massive pulse of fresh water released from a glacial lake in North America, as the ice sheet retreated, flooded into the North Atlantic, disrupted the ocean circulation system that carries warm water from the tropics toward high latitudes. The Atlantic meridional overturning circulation, the great conveyor belt of ocean currents that helps keep Northern Europe warm and regulates global climate patterns, effectively shut down. Without that warm current, temperatures across the Northern Hemisphere dropped rapidly. The cooling lasted until the freshwater pulse dissipated and the circulation restarted. This is the meltwater hypothesis. The physics is sound, the mechanism is real. Freshwater disruption of thermohaline circulation has been demonstrated in both models and observational data, and for decades it was considered sufficient. Then the physical evidence began arriving, and the physical evidence told a different story. In 2007, a team of 26 researchers from multiple institutions published a paper describing a discovery that did not fit the meltwater model at all. Across North America, in a sediment layer dated precisely to 12,800 years ago, they found nanodiamonds, tiny crystals of carbon, some only billionths of a meter across, that form only under conditions of extreme pressure and temperature. You cannot make nanodiamonds with a volcanic eruption. You cannot make them with a flood. You cannot make them with a climate shift, or an earthquake, or any geological process that operates at the pressures and temperatures available on Earth's surface. There is a very short list of natural mechanisms capable of producing nanodiamonds at that concentration and distribution. That list has one entry: a high-velocity extraterrestrial impact. The force of an asteroid or comet fragment striking Earth at tens of kilometers per second generates pressures and temperatures high enough to convert carbon into its diamond crystal structure instantly. The resulting nanodiamonds are ejected into the atmosphere and distributed widely by the blast wave and atmospheric circulation. The initial discovery was dramatic enough, but what followed over the next 15 years made it impossible to dismiss as a local anomaly. Nanodiamonds from the same time horizon were found at more sites, then more still. By 2020, the evidence had been replicated at more than 50 separate locations across 4 continents: North America, Europe, Asia, and the Middle East, all in the same stratigraphic layer, all dated to the same narrow window, around 12,800 years before present. Not approximately the same window, the same layer. In geology, that kind of synchronicity means one event, not several. And along with the nanodiamonds, researchers found other markers that told the same story: magnetic microspherules, tiny spheres of iron, and other metals that form when rock or soil melts rapidly at extreme temperatures and then solidifies while cooling in mid-air. These spherules are a well-established signature of impact events. They were found in the same layer, at the same sites, in concentrations far above background. Iridium, a metal rare on Earth's surface, but relatively abundant in asteroids and comets. Elevated iridium concentrations in a global sediment layer were the signature Luis and Walter Alvarez used in 1980 to identify the asteroid impact that killed the dinosaurs 66 million years ago. Iridium enrichment was found in the Younger Dryas boundary layer, not at the same concentrations as the dinosaur-killing impact. That was a much larger event, but at levels significantly above background, statistically significant, demanding explanation. Shocked quartz. Grains of quartz, deformed by pressures far beyond anything produced by normal terrestrial geological processes. Shocked quartz forms only under the instantaneous extreme pressures generated by a hypervelocity impact or a nuclear detonation. It was found at Younger Dryas boundary sites. And then there was charcoal. Huge concentrations of charcoal in the same layer, spread across multiple continents, indicating widespread simultaneous fires, not localized wildfires. Continental scale burning events that left a carbon signature in sediment across thousands of kilometers. Every one of these markers, nanodiamonds, magnetic microspherules, iridium enrichment, shocked quartz, and widespread charcoal, is individually consistent with a cosmic impact. Taken together, they form a pattern with only one known cause. Something hit Earth 12,800 years ago, and it hit hard enough to distribute ejected material across 4 continents simultaneously. Then, in 2018, the same year Schmidt and Frank published the Silurian hypothesis, a completely independent research team announced a discovery that gave the impact hypothesis something it had previously lacked: a crater. Using airborne ice-penetrating radar, scientists identified a structure beneath the Hiawatha Glacier in northwestern Greenland, a circular depression 31 kilometers across, buried under 900 meters of ice. The structure had all the morphological hallmarks of an impact crater: a raised rim, a central peak, the characteristic geometry produced when a massive object strikes a surface at cosmic velocity. The crater had been hidden beneath the ice sheet so long that no one knew it existed until radar technology became sensitive enough to see through nearly a kilometer of frozen water. Initial analyses suggested the impact occurred roughly 12,800 years ago. Think about what that means physically. A rock or comet fragment, large enough to excavate a hole 31 kilometers wide, struck the northern ice sheet at precisely the moment the world was ending. The energy released by such an impact would have been staggering. Billions of tons of ice vaporized instantly. Superheated steam and pulverized rock blasted into the upper atmosphere. A shock wave raced outward at hypersonic speed across the ice sheet and surrounding land. The thermal pulse from the impact would have ignited fires across hundreds or even thousands of kilometers. The material lofted into the atmosphere would have been distributed globally within days, carried by stratospheric winds and deposited in a thin layer across every continent. Exactly the layer the researchers found, with exactly the markers the researchers documented. The dating of the Hiawatha crater has since been debated. Some later analyses have proposed an older formation date, potentially placing the impact tens of thousands of years earlier than the Younger Dryas boundary. That debate is legitimate and ongoing. But here is what it does not change. The crater exists. An impact of that scale in that region was physically possible, and the evidence layer from 12,800 years ago contains exactly the markers such an impact would produce and distribute globally. Even if the Hiawatha crater itself predates the Younger Dryas, the impact evidence in the boundary layer remains. The nanodiamonds are real, the microspherules are real, the iridium is real, the charcoal is real. They do not need one specific crater to validate them. They need an impact, and impacts on ice do not always leave durable craters, because the ice melts, flows, and reforms. Now consider what was living on the surface of North America when this happened. The Clovis people, named for the distinctive stone spear points, first discovered near Clovis, New Mexico in the 1920s and 1930s. They were the first clearly identifiable widespread human culture in the Americas. Their tool technology, a specific method of shaping stone into thin fluted projectile points of extraordinary precision, has been found at archaeological sites from coast to coast, from southern Canada to Central America. They were not a marginal population clinging to survival at the edge of habitability. They were a successful, well-adapted culture that had spread across an entire continent over thousands of years. They hunted mammoths and mastodons. They had sophisticated tool-making traditions. They thrived in an environment that was, by the standards of Ice Age North America, abundant and productive. And then they vanished. Within one human generation, the distinctive Clovis tool technology disappears from the archaeological record entirely. Not a gradual decline. Not a slow transition into a different tool style. Not a migration pattern that can be traced into a new region. In one stratigraphic layer, they are there. In the next, they are not. The standard explanation for the Clovis disappearance is overkill. Human hunters drove the megafauna to extinction. The food web collapsed. The culture that depended on those animals could no longer sustain itself. That explanation is coherent on paper, and it has one critical problem. Overkill is gradual. It takes generations. It leaves a trail of declining animal populations, shifting hunting strategies. Evidence of dietary adaptation as preferred prey becomes rare. The Clovis disappearance does not show those signatures. It aligns, within the resolution of available dating methods, with the impact evidence layer. One boundary, one moment. Everything changes at once. And the Clovis were not the only ones who disappeared. This is the element that transforms the Younger Dryas from a regional climate story into a global catastrophe. In that same narrow window, around 12,800 years ago, the megafauna of North America went extinct. Mammoths, mastodons, horses, camels, giant ground sloths, short-faced bears, dire wolves, saber-toothed cats, an entire ecosystem of large-bodied animals that had survived multiple previous climate shifts over hundreds of thousands of years, gone. At the same time, woolly mammoth populations across Eurasia declined sharply. Large fauna in South America experienced parallel extinctions in the same interval. The same pattern repeating across ecosystems that had no contact with each other, no shared human population, no mechanism for transmitting hunting pressure from one hemisphere to another. Hunting pressure is inherently local. A human population in what is now Arizona driving mastodons toward extinction cannot simultaneously affect woolly mammoth herds in what is now Siberia. These populations were separated by oceans and thousands of kilometers of ice. Whatever reached them all at roughly the same moment was not a hunting strategy. It was not a slow climate shift. It was something that did not care which continent it struck. Synchronized global extinction requires a synchronized global cause. The meltwater hypothesis provides a regional cooling mechanism for the northern hemisphere. Regional cooling does not explain 4 continents losing their largest animals in the same geological instant. An impact event does. An impact large enough to distribute ejecta globally, ignite continental-scale fires, collapse food webs through the destruction of vegetation, and the disruption of atmospheric chemistry that does. The evidence is in the layer. The nanodiamonds are in the layer. The fires are in the layer. The extinctions are in the layer. And institutional consensus still treats the meltwater hypothesis as the primary explanation and the impact evidence as a fringe alternative. Here is why that matters beyond academic debate. The meltwater hypothesis has been the dominant explanation since the 1980s. Decades of papers have been built on it. Careers have been constructed around it. Funding has been allocated to research programs that assume it. When impact evidence began appearing in the early 2000s, it did not enter a neutral environment. It entered a field where the old explanation already had institutional momentum, where the researchers best positioned to evaluate the new evidence were often the same researchers whose professional identities were built on the old explanation. This is not a conspiracy. It is a structural problem. It is the same structural problem that explains the silence around the Silurian hypothesis, the same asymmetry of incentives, the same career risk calculation. If you challenge the consensus and you are right, you rewrite a chapter of Earth's history. If you challenge the consensus and you are wrong, your career suffers damage that no later paper can fully repair. If you do not challenge the consensus at all, nothing happens to you. The result is that the explanation accounting for less of the physical evidence maintains institutional dominance, not because the evidence supports it more strongly, but because the institutional cost of replacing it is higher than the institutional cost of leaving the gap unresolved. Science is supposed to prefer the explanation that accounts for the most evidence with the fewest additional assumptions. By that standard, the impact hypothesis should be the leading candidate. It accounts for the nanodiamonds, the microspherules, the iridium, the charcoal, the synchronized extinctions across 4 continents, and the abrupt disappearance of the Clovis culture. The meltwater hypothesis accounts for the cooling. One explanation covers everything. The other covers one piece, and the one that covers one piece is still the consensus. Something hit this planet 12,800 years ago. It burned continents. It killed species that had survived every previous ice age cycle for hundreds of thousands of years. It erased a human culture from the archaeological record in a single generation, and the evidence for it has been sitting in a sediment layer across 4 continents, waiting for someone to connect the dots. In the next chapter, we travel to a hilltop in southeastern Turkey, where someone did connect the dots 12,000 years ago, not with scientific instruments, but with stone, enormous carved pillars encoding a message so precise that researchers did not recognize what it was saying until 2017. A date, a warning, a memory carved into limestone, and then deliberately buried underground to survive whatever came next. What do you build when you have just watched the world end? Not a shelter, not a wall, not a food storehouse, not a fortress against enemies. Those are the things you build when you expect the same world to continue. But when the world itself has ended, when the sky has done something that killed nearly everything you knew, when the survivors are standing in a landscape they no longer recognize, the thing you build is different. You build a record. You build something that will survive the next catastrophe, and the one after that. You build it large enough that whoever comes after cannot miss it. And you build it in stone, because stone is the only material that outlasts everything human hands can destroy. Roughly 11,500 years before the current era, on a limestone ridge in what is now southeastern Turkey, somebody began building the most sophisticated structure on Earth. 6,000 years before Stonehenge, 7,000 years before the Egyptian pyramids. In an era when, according to every standard model of prehistoric development, no human population on the planet should have been capable of organized monumental construction. The site is called Göbekli Tepe. Here is what the standard timeline says about the people who built it. They were hunter-gatherers. They had no agriculture. They had no permanent settlements. They had no writing, no administrative structure, no state, no organized labor system. By every conventional measure of civilizational development, they were not supposed to be capable of doing what they did. And yet the physical evidence proves they did it. The site consists of at least 20 circular enclosures, each containing multiple T-shaped limestone pillars. The largest pillars stand over 5 meters tall and weigh up to 10 tons. They were quarried from bedrock, roughly 500 meters from their final positions, transported without wheels, without draft animals, without any of the mechanical advantages later civilizations would develop, and raised into place with a precision that modern structural engineers find impressive. The pillars are not blank, they are carved. Animals rendered in high relief cover their surfaces: foxes, serpents, scorpions, vultures, wild boar, cranes. The carvings are not crude, they are detailed, proportional, executed with a sophistication, implying a mature artistic tradition, stretching back generations before the site itself was constructed. The total area of the excavated portions covers roughly 90,000 square meters, and ground-penetrating radar indicates that what has been excavated so far represents less than 5% of the total complex. The vast majority of Göbekli Tepe remains underground, unexcavated, waiting. The logistical requirements of this construction are staggering when compared to the assumed capabilities of its builders. Quarrying and shaping 10-ton limestone pillars requires sustained effort by skilled workers. Transporting those pillars 500 meters across uneven ground without wheeled vehicles requires coordinated teams of dozens of people working in organized shifts. Raising the pillars into vertical positions and placing them with geometric precision inside carefully planned circular enclosures requires engineering knowledge, planning, and some kind of command structure capable of directing complex multi-stage projects over extended periods of time. And every one of those workers needed to be fed. Hunter-gatherer societies, by definition, obtain food through hunting and foraging. These activities require mobility. They require the population to follow the food. They do not naturally produce the caloric surplus needed to support a large stationary workforce engaged in non-subsistence labor for months or years at a time. Klaus Schmidt, the German archaeologist who excavated Göbekli Tepe for 2 decades until his death in 2014, proposed a resolution to this contradiction that turned the standard model of civilization upside down. He argued that the construction itself drove the invention of agriculture. The workforce needed food. Feeding the workforce required cultivating grain. The temple came first. Agriculture followed. If Schmidt was right, and no one has successfully refuted his argument, then everything we thought we knew about the sequence of human development is backward. We assumed agriculture came first. That surplus food enabled permanent settlements. That permanent settlements enabled social organization. And that social organization eventually produced the capacity for monumental construction. Göbekli Tepe says the opposite. Something motivated people to build before any of those preconditions existed. Something so urgent, so important, that it justified the invention of agriculture itself as a support system for the construction project. What was that something? What was so important that it came before and caused farming? The answer may be carved on Pillar 43. Pillar 43, often called the Vulture Stone, is one of the most heavily decorated pillars at the site. Its surface carries a complex arrangement of animal figures: a vulture with one wing raised, a scorpion beneath it, a headless human figure, a disc above the vulture that could represent the sun. Other animals arranged around the central figures in positions that seem deliberate, purposeful, encoded with information the carvers expected someone to understand. For decades, the imagery was interpreted as mythological, perhaps a hunting scene, perhaps a religious narrative, perhaps a funerary ritual. Generic categories assigned to carvings, whose meaning had not been deciphered because no one had applied the right analytical framework. In 2017, researchers at the University of Edinburgh published a study that changed the interpretation entirely. They treated the animal figures not as mythological symbols, but as representations of star constellations. Using astronomical software capable of modeling the positions of stars as seen from any point on Earth at any date in the past, they mapped the animal figures against the actual night sky and searched for a date when the configuration matched. The match they found was precise. The arrangement of figures on Pillar 43 corresponds to the positions of constellations as they appeared in the sky, approximately 10,950 years before the current era. That date falls at the onset of the Younger Dryas, the beginning of the catastrophe, the moment the world ended. The researchers concluded that Pillar 43 is not a mythological scene. It is an astronomical record, a date stamp, the most important date in the history of the people who carved it, encoded in a format that does not depend on language, does not depend on cultural continuity, and does not degrade over time. The positions of stars change slowly and predictably due to the precession of Earth's rotational axis, a cycle lasting roughly 26,000 years. Any civilization with basic astronomical knowledge and the mathematical tools to calculate precession can read the date encoded on Pillar 43. The message was not written for the people who carved it. They already knew what had happened. The message was written for whoever came later, for us. They encoded the date of the catastrophe in the only universal language available to them, the geometry of the sky itself, and preserved it in the only medium that survives geological and civilizational collapse. Stone. That is not decoration. That is not myth. That is communication aimed across thousands of years at an audience the builders knew they would never meet, calculated to survive every possible scenario except the destruction of the stone itself. And then they buried it. This is the detail most accounts of Göbekli Tepe mention, without fully absorbing what it means. The site was not abandoned. It was not gradually covered by natural sediment accumulation over millennia. The people who built it, or their immediate descendants, deliberately and systematically filled the enclosures with rubble, soil, and debris. They sealed the entire complex beneath meters of compacted fill. They covered what they had spent generations constructing, and then they walked away. Why would you bury something that took that much effort to build? There is only one answer that makes sense of the effort involved. You bury it to protect it. You bury it because you have seen what happens to things left on the surface when the sky falls. You bury it because a structure above ground is vulnerable to fire, blast waves, and the environmental chaos that follows a catastrophic event. A structure under 3 meters of compacted fill survives almost anything. Impact debris, continental fires, centuries of climate chaos, even the total collapse of whatever civilization comes after. They were not building for themselves. They were building for whoever came after them. The entire site is a message sealed in stone and buried underground, designed to survive the next catastrophe and be found by whoever was still alive to dig it up. We found it. We are still arguing about what it means, but the astronomical encoding on Pillar 43 has been published, peer-reviewed, and replicated. The date is there. The message is there. The question is whether we are willing to hear what it says. Now travel 1,500 kilometers south to the Giza Plateau in Egypt, where another stone structure sits with its face pointed due east toward the rising sun. The Great Sphinx, a lion-bodied monument carved from the living bedrock of the plateau, the largest monolithic sculpture on Earth. Orthodox dating places its construction at approximately 2500 BCE during the reign of Pharaoh Khafre of the 4th dynasty. That dating is based on historical records and stylistic association with other nearby structures from the same period. It is not based on any direct physical measurement of the Sphinx itself. In 1990, Robert Schoch, a geologist with a doctorate from Yale, examined the limestone walls of the enclosure surrounding the Sphinx. What he found was a pattern of erosion that did not fit the expected age of the structure. The walls displayed deep vertical weathering channels, the specific pattern produced by prolonged exposure to heavy rainfall running down vertical stone surfaces over centuries. Not wind erosion, which produces horizontal scouring. Not sand abrasion, which produces a different surface texture entirely. Rain. Sustained. Repeated. Heavy rainfall over a long period of time. Egypt has not experienced that kind of rainfall since before 5000 BCE. The last period of sustained heavy precipitation in the region ended roughly 7,000 years ago, when the climate shifted and the Sahara transitioned from a green, fertile landscape into the desert it is today. If the erosion on the Sphinx enclosure was caused by rainfall, then the structure must have been exposed to that rainfall, which means it must have existed before the rainfall ended, which means it was carved before 5000 BCE, at minimum 2,500 years older than the orthodox dating, and possibly much older than that. Now add the astronomical alignment. The Sphinx faces due east. On the spring equinox, the constellation rising on the eastern horizon changes over time because of the precession of Earth's axis. At 2500 BCE, the official date of the Sphinx, the constellation rising on the eastern horizon at the spring equinox was Taurus, the bull. The Sphinx is not a bull. At 10,500 BCE, the constellation rising on the spring equinox was Leo, the lion. The Sphinx is a lion. At that date, it would have been staring directly at its own celestial counterpart rising above the horizon. Two independent lines of evidence, one geological, one astronomical, both point away from the orthodox date and toward a much older origin. They do not converge on exactly the same year, but both indicate a period thousands of years before dynastic Egyptian history begins. And if the Sphinx is that old, then where is the civilization that built it? Where are their other structures, their tools, their settlements? The answer is the same answer Frank and Schmidt gave us. Gone. Erased by 7,000 or more years of geological processing, climate change, and sea level rise. Any coastal settlements from that era now sit under tens of meters of water in the Mediterranean and Red Sea. The absence of corroborating evidence is not evidence against the geological argument. It is exactly what the geological argument predicts. Now consider what the body of the Sphinx tells you about its own history. The proportions are wrong. The body is massive, stretching over 73 meters in length. The head is visibly, obviously, disproportionately small relative to the body. This disproportion is not subtle. Anyone looking at the structure without prior assumptions can see it. The most widely accepted explanation, endorsed by many mainstream Egyptologists, is that the head was recarved. The original head, whatever it depicted, weathered badly during an extended period of exposure. When pharaohs of the Old Kingdom encountered the structure, the original head was significantly eroded. They recarved it into the image of a pharaoh, reducing its size in the process, because they had to work within the diminished volume of weathered stone. If the head was recarved, then the original is gone. Whatever the Sphinx originally depicted has been lost, but the body remains. The enclosure walls remain, the geological weathering remains, and the astronomical alignment remains. Someone, before the historical record of Egypt begins, carved a lion-bodied monument from the bedrock of the Giza Plateau, and aligned it precisely toward the point on the horizon where Leo rose at the spring equinox. Whoever they were, they possessed astronomical knowledge sophisticated enough to encode a specific celestial alignment into the orientation of a massive stone monument, and they left no name, no text, no inscription we have found connecting them to the structure. The gap between knowledge and action is not new in human history, but the gap between knowledge and action, when that knowledge includes a direct geological precedent for civilizational collapse, is something humanity has never faced before. We are the first, and what we do with that distinction will determine what the next reader of the geological record finds when they examine our layer, because there will be a next reader. That is one of the few certainties in this entire story. Earth will not stop being habitable. Even the PTM, as devastating as it was temporary. The planet recovered. Life continued. New species filled the niches left vacant by extinctions. New ecosystems assembled themselves from the survivors. Given enough time, measured in tens of millions of years, which Earth still has ahead of it before the sun begins expanding into a red giant, the conditions for complex life will reassert themselves. Intelligence may appear again, perhaps from primates, perhaps from corvids, perhaps from cephalopods, perhaps from a lineage we cannot predict. And when it does, when the next species with the cognitive capacity to read chemistry develops the instruments to analyze ancient rock, they will find our layer, a thin band of isotopically light carbon, a sharp negative excursion in the carbon-13 ratio, anomalous concentrations of trace metals at specific global locations, a possible radioactive signature requiring explanation. They will study it the way we study the PTM. They will model natural mechanisms. They will calculate the volume and discover, as we have discovered, that the numbers do not quite add up. Some researcher among them, someone with the intellectual courage Gavin Schmidt and Adam Frank showed in 2018, will publish the formal question: could this layer represent the output of an industrial civilization that existed at this point in Earth's history? They will run the same model Schmidt and Frank ran. They will reach the same conclusion. We would not be able to tell, and they will look at the chemistry in our layer and note that it fits. Then they will wait for the response from their field, and if their institutional structures resemble ours at all, the response will be the same: acknowledgement, citation, silence, because the conclusion is uncomfortable, because admitting that something existed before them means admitting that the universe runs this experiment more than once, and that running it more than once does not guarantee a different result. We are going to become someone else's unanswered question, someone else's gap in the literature, someone else's uncomfortable hypothesis, sitting in a journal with a handful of citations and years of institutional silence. The only thing we do not know is whether they will ask the question because we left only the chemical layer, or because we left the chemical layer and survived long enough to leave something more. What separates those two outcomes is not technology, it is not intelligence, it is not even knowledge, because we already possess the knowledge. What separates them is what we choose to do with that knowledge, in the brief window between recognizing the pattern and the pattern completing itself. That window is now, not a century from now, not next decade. The feedbacks are activating, the trajectory is set. The distance between where we are and where the PTM crossed its threshold is measured not in centuries, but in the decisions made by the generation currently alive. This generation, the one listening to these words, the one that knows, with a certainty no previous generation has possessed, exactly what it is writing into the rock. Something may have been here before us, maybe. The data fits, the gaps are real, the framework connecting them has been published, peer-reviewed, and largely ignored. That is the honest state of the evidence, not a conclusion, not a verdict. An open question, whose openness itself says something about how we handle ideas. Challenging the story we prefer to tell ourselves about our place in Earth's history. But here is what is not maybe. Here is what is confirmed, measured, replicated, and beyond any reasonable dispute. The geological record makes no exceptions. It has processed every civilization, every species, every ecosystem that has ever existed on this planet, with the same indifference. Chemistry survives. Everything else decays. Whatever came before us, if anything did, left a layer. And that layer either has an explanation we have found, or one we have not found yet, or one that makes us deeply uncomfortable because of what it implies. We are leaving a layer right now. Think about what that means. Not abstractly, not metaphorically, physically. The carbon from your car's exhaust, the carbon from the power plant that charged the device you are listening on, the carbon from the factory that made the food you ate this morning. Every molecule of that carbon carries an isotopic fingerprint. Light carbon, carbon-12 enriched, the unmistakable chemical signature of burned ancient biological material. That carbon enters the atmosphere. It dissolves into the ocean. It is incorporated into the calcium carbonate shells of microscopic marine organisms living in surface waters. Those organisms die. Their shells drift downward through thousands of meters of darkness to the seabed. They accumulate in sediment that compresses over millions of years into limestone. And the isotopic fingerprint of the carbon they incorporated is preserved in that stone permanently, written into the geological record with a fidelity no human archive, no digital storage system, no library can ever match. Rock does not forget. Rock does not interpret. Rock records, and what it is recording right now, at this very moment, in sediment accumulating on the floors of every ocean on Earth, is us, our energy choices, our consumption patterns, our collective decision about how much ancient carbon to extract and burn in the brief window of time we occupy. The layer is being written, the fingerprint is being set, and once it is in the rock, it stays there as long as the rock exists. Here is the inventory of everything we will leave behind that a future reader could detect after 50 million years of geological processing. A carbon isotope excursion, a sharp negative shift in the carbon-13 ratio, globally distributed, rapid in onset, large enough to be clearly distinguishable from background variation. This will be the clearest and most durable signal of our existence. It will outlast every building, every road, every satellite, every work of art, every written record. The last thing to survive of human civilization will be the chemical evidence of the carbon we burned. Anomalous trace metal concentrations, at the locations where our cities stood, where our mines operated, where our industrial facilities processed material. Certain metals will be concentrated in a thin sediment layer above natural background distribution: lead, copper, zinc, rare earth elements, cadmium, mercury. These concentrations will persist as subtle anomalies in the rock. A future geochemist with sufficiently precise instruments could detect them, but without context, without any surviving structure or artifact to connect chemistry to culture, those anomalies will look like natural mineral deposits. They will be catalogued. They will not be understood. A possible radioactive signature. The isotopes from nuclear testing and nuclear energy production have half-lives ranging from thousands to millions of years. After 50 million years, even the longest-lived products will have decayed to levels difficult to distinguish from natural background radiation. But some anomalous isotope ratios at specific sites, reactors, detonations, might persist as faint, puzzling readings in the rock. Without a framework for interpretation, they will remain puzzling. That is the complete list. Carbon chemistry, trace metals, a faint whisper of radiation, no structures, no artifacts, no images, no language, no names, no indication that the entities who produced these chemical signals were aware of their own existence, let alone capable of contemplating the permanence of the record they were writing. Just numbers in a thin band of rock. Now look at what the PTM left behind. A carbon isotope excursion, a sharp negative shift in the carbon-13 ratio, globally distributed, rapid in onset, with a volume exceeding known natural explanations. Anomalous trace conditions in the boundary layer still being catalogued and characterized. A chemical record studied for 30 years and still containing a gap no one has closed. The inventory is the same, the fingerprint is the same, the format is the same. The only difference is 56 million years of time and the unresolved question of whether the entity that left the earlier signal knew what it was doing. We know what we are doing. That is the line that separates us from every previous entry in the geological record. We are the first civilization in Earth's history possessing the instruments to measure its own impact on planetary chemistry in real time. We are the first to read the record of what came before us and understand the implications. We are the first to build the models predicting where the current trajectory leads. We are the first to have the Silurian hypothesis in a peer-reviewed journal, explicitly telling us that a vanished civilization's footprint would look exactly like the anomalies we find in ancient rock. We are the first to see the pattern, and seeing the pattern has not changed the pattern. That is the fact at the center of this entire story. Not the PTM, not the Younger Dryas, not Göbekli Tepe, or the Sphinx, or the underground cities, or the flood myths, or the drowned coastlines. All of those are pieces of a puzzle whose shape we can now describe clearly enough to recognize. The piece defining this moment, the piece determining what our layer will say to whoever reads it, is the gap between knowing and acting. We have crossed the threshold of knowledge. We have not crossed the threshold of response. Think about the people who built Göbekli Tepe. They had just survived the end of a world. They had watched the sky do something catastrophic. They had lost people, communities, entire ways of life. And their response was to build, not for themselves, but for whoever came next. They encoded the date of the catastrophe in the geometry of the stars. They carved it into 10-ton stone pillars. They organized hundreds of people, invented agriculture to feed them, and spent generations constructing a message they knew they would never see delivered. Then they buried it to make sure it survived. They did not have writing. They did not have metal tools. They did not have any of the advantages we take for granted. What they had was knowledge of what had happened, and the conviction that someone in the future needed to know it too. They acted on that knowledge with everything they had. They left a message in stone that lasted 12,000 years and was only rediscovered in 1994. 12,000 years. A message in stone from people with no advanced technology, no institutional support, no industrial infrastructure. Designed, built, and preserved with nothing but human labor and the absolute certainty that the information mattered enough to justify the cost. Now look at us. We have the information, we have the technology, we have the institutions, the scientific knowledge, the computational power, the engineering capacity, and the global communications networks to act on what we know at a scale and speed the builders of Göbekli Tepe could never have imagined. And the layer we are writing into the rock says we are not acting. The carbon curve is still rising. The feedbacks are still activating. The trajectory has not changed. The layer is getting deeper. What will it say about us? That is the question this story leaves you with. Not whether something existed before us. That question may never be answered with certainty, because the geological record is structurally incapable of preserving the answer. The question that matters, the question that has a definite answer being written right now, is what our layer will say about us. Will it say we were the first civilization to recognize the pattern and change course? That we saw our own fingerprint in the rock of deep time and chose a different trajectory? That knowledge made a difference? Or will it say what the PTM layer says? A spike, a warming, an extinction horizon, and then slowly over 200,000 years a recovery, with no indication that whatever produced the signal survived long enough to see the planet stabilize. The Milankovitch cycles will continue. Earth's orbital parameters will shift on their long, predictable schedules, adjusting the energy balance of the climate system over tens of thousands of years. The next glacial period will eventually arrive, regardless of what we do. The planet will continue its geological processes, its tectonic recycling, its slow reshaping of continents and ocean basins. In 100 million years, Earth's geography will be unrecognizable. Continents will have drifted into new configurations. Ocean basins will have reshaped themselves. The rock we are writing our signal into will have been folded, uplifted, subducted, compressed, and rearranged by forces operating on timescales so vast that human civilization occupies less than a single pixel in the image. But the chemistry will survive. Somewhere in a layer of limestone that was once sediment at the bottom of a Paleogene ocean, the isotopic signature of our carbon will persist. Light carbon, rapid, global, with a fingerprint pointing unmistakably to burned biological material. It will be there when the next reader arrives. It will be there when someone develops the instruments to analyze it. It will be there when someone asks the question, what was this? What caused this? What happened to whatever produced it? And the answer to that question, the one we are writing right now, is not yet finished. It is being composed in every power plant that fires up, in every forest that burns, in every policy decision delaying transition, in every barrel of oil extracted and burned, and in every choice, every investment, every demand, every vote that either accelerates the trajectory or bends it towards something other than what the PTM trajectory produced. The layer is not sealed. The entry is not complete. The last line has not been written. Something may have been here before us. We do not know what it was. We do not know if it understood what it was doing. We do not know if it saw the threshold coming, or crossed it in ignorance. We do not know if it left a warning. We do not know whether we would recognize that warning if it did. But we know what the record shows. A fingerprint, a gap, a temperature spike, an extinction, and a 200,000-year silence before the planet found balance again. We are not going to be a mystery to whoever comes next. We are going to be a data point. A layer of chemistry with a fingerprint they will recognize, because it will look exactly like the one we have spent 30 years studying and 6 chapters discussing. The only variable still open, the only thing separating a layer that tells a story of recognition and change from one that tells a story of recognition and repetition, is what we do between the moment we understand the pattern and the moment the pattern completes itself. The builders of Göbekli Tepe understood something we have been slow to learn. Knowledge that is not acted upon is not really knowledge. It is decoration. They knew the sky had fallen. They built in response. They carved the date into stone. They buried it underground. They spent generations and invented agriculture to make sure the message survived. They did not have our advantages. They did not have our resources. They did not have our understanding of the mechanisms. What they had was the clarity that comes from having lost everything, and the resolve to make sure the loss was not meaningless. We have not lost everything. Not yet. And whether or not we do depends on whether we treat the pattern as information or as a warning. The rock is waiting. The layer is being written. The fingerprint is being set. And somewhere, 50 million years from now, someone is going to find it. Hold this question in your mind as you leave this story. Not the question of what was here before us. The question of what we want our layer to say. Because the record is patient. The record does not judge. The record does not hope. It simply records what happened in the chemistry of ancient rock, with a fidelity nothing else in the universe can match. And the entry it is recording right now, the one that will carry our name, whether we intended it to or not, is still 700 kilometers to the north, in the region called Cappadocia in central Turkey. The evidence of ancient catastrophic knowledge takes an entirely different form. Not monuments above ground, but cities beneath it. Derinkuyu is the largest currently known underground settlement in the region. It extends 18 levels below the surface. It was designed to house approximately 20,000 people. It has ventilation shafts reaching from more than 60 meters underground to the surface, independent wells accessing the water table, stables for livestock, storage rooms capable of holding years of food, rolling stone doors weighing hundreds of kilograms that could seal individual tunnel sections from the inside, creating airtight barriers between levels. A complete self-contained environment capable of sustaining a large population with zero contact with the surface for extended periods. There are more than 200 similar underground settlements in the Cappadocia region. Some are connected by tunnels extending for kilometers. The official explanation attributes them to defense against historical invaders. And that explanation works for 3 levels, maybe 5. It does not work for 18. No army in the historical record of that region ever chased defenders 18 levels underground. The logistics are impossible. The darkness alone would stop them. 3 to 5 levels provides total protection against any human military threat. What justifies the remaining 13? Distance from the surface, more rock between you and whatever is happening above, independent air supply capable of filtering contaminated atmosphere, multi-year food storage, complete surface independence. You build this when the threat is not soldiers. You build it when the surface itself becomes uninhabitable, when the air is poisoned by ash or chemical fallout, when the sun is blocked for months or years, when temperatures drop so far that agriculture becomes impossible, when everything that sustained life above ground collapses and will not recover for years. These are not threats that appear in the historical record of Cappadocia. These are the threats that appear in the historical record of 12,800 years ago. The people who built Göbekli Tepe encoded the date of the catastrophe in stone and buried it to survive the next one. The people who may have carved the Sphinx aligned it with a constellation marking a specific epoch in deep time. The people who built Derinkuyu engineered a survival system designed to outlast the total collapse of surface conditions. 3 sites, 3 different responses to the same knowledge. The knowledge that the world had ended once, violently, from above, and that it could end again. In the next chapter, we follow the memory of that catastrophe as it spread across every inhabited continent, compressed into the oldest stories humanity possesses. Stories that 500 independent cultures tell in nearly identical terms. A flood that ended the previous world, and a coastline that modern marine geology confirms is sitting exactly where those stories say it should be, under 120 meters of ocean. More than 500 cultures on every inhabited continent on Earth tell a story about a flood. Not just any flood. The flood, a cataclysm that ended the previous world. Water that rose without warning, or with barely enough warning for a chosen few to survive. A world before the water, and a different world after it. These stories come from Mesopotamia, from the Hebrew Bible, from Hindu scripture, from the oral traditions of Aboriginal Australians, from the mythology of the Aztecs and the Maya, from the legends of the Hopi, the Cree, the Inuit, from Chinese, Korean, and Japanese folklore, from the island cultures of the Pacific, from the tribal narratives of sub-Saharan Africa. 500 independent versions, documented by anthropologists and folklorists across 3 centuries of fieldwork, in cultures that had no documented contact with each other, separated by oceans, by continents, by thousands of years of independent development, all telling the same story. The standard academic explanation is straightforward. Floods are a universal human experience. Every civilization settles near water. Every civilization experiences flooding. The flood myth, therefore, is a natural response to a recurring natural phenomenon. That explanation sounds reasonable. It is also incomplete, because 500 cultures did not independently invent the same specific narrative structure. The flood myths do not merely describe rivers overflowing their banks or storm surges swamping villages. They describe a sequence, a previous world that existed before the water, a catastrophic inundation so total that it redefined the boundary between the old reality and the new one. A survivor, often warned in advance, who preserves life or knowledge through the deluge. A new beginning on the other side. That is not a generic flood story. That is an account of a specific category of event, with a specific narrative architecture, and when 500 independent sources across every inhabited continent describe the same sequence, the explanation that they all invented it separately requires a more extraordinary coincidence than the explanation that they all remember the same thing, or at least the same category of thing. Because what geology tells us happened between 15,000 and 7,000 years ago is exactly the kind of event that would leave such a memory in every coastal culture on Earth. Here is the number most people have never been asked to hold in their minds. 120 meters. That is how much global sea level rose between the end of the last ice age and the stabilization of modern coastlines. 120 meters. Roughly the height of a 40-story building. An entire vertical column of ocean that did not exist on the continental shelves during the Ice Age, and does exist there now. That rise was not a single event. It unfolded over approximately 8,000 years, between roughly 15,000 and 7,000 years ago, driven by the melting of the massive ice sheets that covered much of North America, northern Europe, and parts of Asia during the last glacial maximum. But the rise was not steady. It came in pulses. Periods of relative stability interrupted by rapid surges when large sections of ice sheet collapsed into the ocean. One of the most dramatic of these pulses, known as Meltwater Pulse 1A, occurred around 14,000 years ago. In only a few centuries, sea levels jumped by roughly 20 meters. 20 meters in a few hundred years. Another major pulse may have coincided with the events of the Younger Dryas, 12,800 years ago, when the catastrophe we discussed in the previous chapters could have destabilized ice sheets and triggered rapid coastal flooding in multiple regions simultaneously. To understand what 120 meters of sea level rise means in human terms, stop thinking of it as a number and start thinking of it as a landscape. During the Ice Age, the coastlines of every continent were miles farther out than they are today. The continental shelves, the shallow underwater platforms that extend from the present shoreline out to the deep ocean, were dry land. Rivers flowed across them, forests grew on them, animals grazed on them, and humans lived on them, not in tiny numbers. Coastal zones are the most productive environments on Earth. They provide access to marine protein, fresh water from river deltas, fertile soil from alluvial deposits, and natural transportation corridors along waterways. In every period of human history for which we have detailed records, the largest and most complex settlements have been coastal. There is no reason to believe the Ice Age was different. The most populated, most developed, most interconnected human communities of the Pleistocene were almost certainly located on the coastal plains and river deltas of the continental shelves, all of which are now underwater. Put yourself on one of those coastlines, 12,000 years before the current era. Your community has existed there for generations. Your grandparents were born there. The stories they told about their grandparents were set there. The geography of your world, your sacred sites, your burial grounds, your fishing territory, your trade routes, your seasonal patterns, all of it is anchored to a landscape you have no reason to believe will ever change. And then the sea starts moving. Not overnight, not in one giant catastrophic wave, though the pulses may have felt catastrophic to those who lived through them. The water advances. Some years the change is barely noticeable. A high tide that reaches farther than last year. A low-lying area near the river mouth that stays flooded longer each spring. Then a pulse hits. The water rises faster. The low ground floods and does not drain. The beach where the children played last summer is a tidal flat this summer, and open water the summer after that. The fishing grounds shift. Freshwater springs near the coast turn brackish and then salt. Your children grow up watching the sea eat the world. Their children grow up in a world already smaller than the one their parents described. And their children grow up with stories of a time before, when the coast was farther out, when the land was wide, when the old places still existed down there, under the water, where you can sometimes see shadows on the seabed, when the light is right and the water is calm. Those stories get told for 1,000 years, then 2,000, then 5. They get compressed. The gradual process of generational coastal loss becomes a single catastrophic event in the retelling, because that is how inherited trauma works in human memory. Complexity collapses into simplicity. A century of rising water becomes a flood that came in a night. The specific geography of lost places becomes a paradise destroyed. The survivors who adapted and moved inland become the chosen few warned by the gods. The narrative crystallizes. The details change in each culture, but the structure remains. A world before, a flood, survivors, a new beginning. 500 versions of that story are not 500 independent inventions. They are the accumulated, compressed, mythologized memory of one of the greatest geographical transformations in human history. The sea swallowed an entire world's worth of coastline. The memory of it outlasted every physical trace of the world that was lost, and geology confirms every element of that memory. The sea level data is precise. It comes from coral cores, coastal sediment analysis, the dating of submerged shoreline features, and the chemistry of marine organisms, whose shells record the salinity and temperature of the waters they grew in. The 120-meter rise is not a guess. It is a measurement replicated by independent methods across multiple ocean basins. The rapid pulses are documented. Meltwater pulse 1A is visible in the coral record, with a distinct acceleration in the rate of rise datable to within a few centuries. The flooding of specific regions has been mapped. The North Sea Basin, which connected Britain to continental Europe as dry walkable land during the Ice Age, a landscape archaeologists call Doggerland, flooded progressively throughout this period. It was a vast low-lying plain crossed by rivers, dotted with lakes, rich in game and plant life. People lived there, hunted there, built communities there. And then, over the course of a few thousand years, the North Sea filled it in. By roughly 8,000 years ago, it was gone. Britain became an island. A landscape the size of a small country vanished beneath the waves. The Black Sea Basin tells a similar story with an even more dramatic ending. During the Ice Age, the Black Sea was a freshwater lake, smaller than it is today and sitting well below the level of the Mediterranean. Around 7,500 years ago, as Mediterranean sea levels rose, water breached the narrow land barrier at what is now the Bosphorus Strait. The breach may have been gradual, or it may have been sudden. Some geological models propose a catastrophic inundation, a wall of salt water pouring through the breach at a rate roughly 200 times the flow of Niagara Falls, flooding the basin and displacing every community settled along its shores. This event has been proposed by marine geologists William Ryan and Walter Pittman as a regional origin point for multiple Near Eastern flood traditions, including the story that later became the biblical account of Noah. Whether or not the Black Sea flood was as sudden as the most dramatic models suggest, the geological fact is not disputed. The basin flooded, the freshwater lake became a saltwater sea, the communities along its shores were displaced, and the memory of that displacement entered the oral traditions of the cultures that survived it. The total land area lost to the ocean between 15,000 and 7,000 years ago was roughly equivalent to the combined landmass of Europe and North America. That is the scale of what disappeared. Not a riverbank, not a delta, a continental expanse of inhabited land, home to thousands of years of human settlement, cultural development, and accumulated knowledge, swallowed by the sea at a pace individual human lifetimes could perceive and remember. And we have barely begun to examine what lies beneath the water, where that land once existed. Underwater archaeology of the continental shelves is one of the most underfunded and underexplored areas in the study of human history. The technology exists: side-scan sonar, remotely operated submersibles, diving operations capable of working at depths of dozens of meters. All of these tools are available, and when they have been deployed, the results have been extraordinary. In the Gulf of Cambay, off the western coast of India, sonar surveys identified what appears to be a submerged settlement at a depth of roughly 40 meters. Geometric patterns on the seabed, consistent with structural foundations. Artifacts recovered from the site have been dated to roughly 9,500 years ago. If confirmed, this would represent one of the oldest urban-scale settlements ever discovered, predating the earliest known cities of Mesopotamia by thousands of years. And it is underwater, buried beneath 4,000 years of marine sediment, in a region that was dry coastal land during the period when the settlement appears to have been occupied. Off the southern coast of Japan, near the island of Yonaguni, divers discovered a massive submerged rock formation, with features some researchers argue are too geometric, too regular, too precisely stepped to be the product of natural geology alone. The Yonaguni Monument, as it has come to be known, remains controversial. Geologists point to natural fracturing processes in the local sandstone that can produce step-like forms. Proponents point to specific features: right-angle cuts, symmetrical terraces, what appear to be carved channels, that they argue exceed what natural fracturing should produce. The debate continues. But the debate itself is revealing. We are arguing over whether a submerged structure off Japan is natural or artificial, while having conducted nothing remotely resembling a comprehensive archaeological survey of the continental shelves where Ice Age coastal civilizations would have lived. Off the coasts of the Mediterranean, researchers have found submerged Neolithic settlements, villages with stone walls, and organized floor plans, sitting on the seabed at depths corresponding to coastline positions from 8,000 to 10,000 years ago. Off the coast of Albania, off the coast of Israel, off the coast of southern France, each discovery treated as an isolated curiosity rather than evidence of a systematic pattern. The pattern being this: the most inhabited coastal zones of the Ice Age world are underwater, and we have explored only a vanishingly small percentage of them. We have spent billions of dollars and decades of effort searching for signs of microbial life on Mars, a planet that has been geologically dead for billions of years, with no atmosphere, no liquid surface water, and no detectable biological history. Meanwhile, the drowned coastlines of our own planet, accessible with current technology, known to have been inhabited by human populations for tens of thousands of years, containing the archaeological record of the coastal civilizations of the Ice Age world, remain largely unexplored. The reasons are not scientific, they are institutional. Underwater archaeology is expensive, logistically complex. It falls between terrestrial archaeology, marine geology, and oceanography. Funding agencies do not have neat categories for it. Academic departments are not structured around it. Career incentives push researchers toward land-based excavation, where methods are established, costs are lower, and publication pipelines are clear. The result is a blind spot the size of a continent. We know the land was there. We know people lived on it. We know the sea took it. We know the memory of that loss survives in the oldest stories humanity possesses, repeated 500 times across every inhabited continent. And we have not seriously looked at what is sitting on the seabed where that land used to be. What are we going to find when we actually do? The flood myths are not evidence of a supernatural event. They are evidence that human populations with oral traditions witnessed geological events large enough to define the boundary between their old world and their new one. Geology confirms those events were real. The myths confirm they were remembered. The question is not whether the stories describe something that happened. Geology settles that. The question is, what else is contained in those memories that geology cannot tell us directly? What knowledge did the people living on those drowned coastlines carry with them when the water forced them inland? What did they know about the world before the flood? What did they preserve? What did they lose? We have now traced a line from the chemistry of 56-million-year-old rock to the oral traditions of cultures remembering a world the ocean swallowed. In the next chapter, we turn the lens inward and confront the most uncomfortable connection of all, the PTM fingerprint and our own. Because the carbon we are pumping into the atmosphere right now carries the same isotopic signature, follows the same trajectory, and is approaching the same thresholds that define the beginning of the most severe climate event in the last 66 million years. And the question no one wants to answer is whether we are watching history repeat itself, or whether we are the ones writing the repetition. Here is the number that turns everything we have discussed from a story about the past into a warning about the present. The rate of carbon dioxide increase in the atmosphere right now, measured in parts per million per year, is faster than at any point in the last 800,000 years of ice core data. Not approximately faster, measurably, unambiguously, record-breakingly faster. The instruments tracking atmospheric composition at the Mauna Loa Observatory in Hawaii, the longest-running continuous measurement of carbon dioxide in Earth's atmosphere, show a concentration that has risen from roughly 280 parts per million before the Industrial Revolution to more than 420 parts per million today, a 50% increase in roughly 2 centuries. And the isotopic signature of that carbon, the fingerprint locked into every molecule of carbon dioxide we have added to the atmosphere, is biological. Light carbon, carbon-12 enriched, the unmistakable chemical marker of burned ancient organic material, coal, oil, natural gas, biological deposits that accumulated in Earth's crust over hundreds of millions of years and were extracted and combusted in a geological instant. The same fingerprint as the PTM. Not similar, not analogous, chemically identical. The carbon-12 to carbon-13 ratio of our industrial emissions falls within the same range as the isotopic excursion recorded in the PTM boundary layer. Geochemist analyzing a sediment sample from the bottom of the ocean 50 million years from now would not be able to distinguish our carbon signal from the one that caused one of the most severe climate events of the past 66 million years. The source is the same, burned biological carbon. The delivery mechanism is the same, rapid release into the atmosphere over a geologically brief window. The isotopic fingerprint is the same, a sharp negative excursion in the carbon-13 ratio, globally distributed, unmistakable, permanent in the geological record. We are not approaching the PTM. We are reproducing it in real time, with full awareness of what we are doing. Now let us be precise about the comparison, because precision matters here. The PTM released between 3 and 7 trillion tons of carbon over a period of roughly 3,000 to 20,000 years, depending on which estimate of the release rate you use. Human industrial activity has released roughly 700 billion tons of carbon since the beginning of the Industrial Revolution. We are not yet at PTM total volumes, but we are at the beginning of the same trajectory. The rate at which we are adding carbon to the atmosphere is comparable to the fastest estimates of the PTM release rate. Some recent analyses suggest our current rate may actually exceed the peak PTM rate, though the uncertainty in the ancient data makes exact comparison difficult. What is not uncertain is the direction. Up, fast, with a matching fingerprint. The temperature projections reinforce the parallel. Global average temperature has already increased by approximately 1.2 degrees Celsius since the pre-industrial baseline. Current trajectories, based on existing emissions commitments and realistic assessments of how quickly the global energy system can transition, project an increase of 2 to 4 degrees by the end of this century. The PTM produced a temperature increase of 5 to 8 degrees over the course of the event. We are already at the low end of that range and accelerating. The question is not whether we will move toward PTM conditions. The question is how far along that path we travel before the feedbacks take control. Because the feedbacks are the part that makes the PTM comparison truly terrifying. The PTM was not caused by one isolated pulse of carbon that then simply dissipated. The initial carbon release, whatever its source, triggered a cascade of secondary releases that amplified and sustained the warming for tens of thousands of years. Warming destabilized methane hydrates on the seafloor, releasing additional greenhouse gases. Warming thawed permafrost in high-latitude regions, releasing stored carbon long locked in frozen soil. Warming reduced ice cover, which reduced planetary reflectivity, which caused the planet to absorb more solar energy, which caused more warming. Each feedback strengthened the others. The system crossed a threshold beyond which warming became self-sustaining, independent of whatever initiated it. And it took 200,000 years for Earth's natural carbon sequestration processes, the slow work of rock weathering and biological burial, to remove the excess carbon from the atmosphere and restore equilibrium. Every one of those feedbacks exists in the current climate system. Every one of them is already showing signs of activation. Permafrost across the Arctic is thawing at rates that exceed the projections of climate models from even a decade ago. The permafrost contains an estimated 1.5 trillion tons of organic carbon, roughly twice the amount currently in the atmosphere. As it thaws, microbial decomposition converts that stored carbon into carbon dioxide and methane, which enter the atmosphere and accelerate the warming that caused the thawing. The feedback loop is already operating. Methane hydrates on the ocean floor remain stable only as long as the water above them stays cold enough. As ocean temperatures rise, the stability boundary shifts. Hydrate destabilization has already been observed in shallow Arctic marine sediments. The total volume of carbon stored in global methane hydrate deposits is estimated at between 1 and 5 trillion tons. If even a fraction of that enters the atmosphere, the effect on global temperature would be measured in degrees, not fractions. Arctic sea ice is declining. Ice reflects roughly 80% of incoming solar radiation back into space. Open ocean absorbs roughly 90%. Every square kilometer of ice replaced by open water converts the surface from a reflector into an absorber. The system warms faster. More ice melts. More open water appears. More heat is absorbed. The albedo feedback has been documented for decades. Its acceleration in recent years has exceeded the predictions of many climate models. And here is the element connecting climate science directly to the Silurian hypothesis and the PTM. We do not know exactly where the tipping points are. We know they exist. We know the PTM crossed one, because the warming sustained itself for 200,000 years after the initial carbon input ended. We know Earth's climate system contains tipping points threshold, beyond which the feedbacks become self-reinforcing, and the system shifts into a new equilibrium, regardless of what triggered the initial change. But we do not know how close we are to those thresholds. We cannot see them from this side. The PTM shows us what the other side looks like. Mass extinction of deep-sea organisms. Acidification of the global ocean. Temperature increases large enough to render large parts of the planet's surface uninhabitable for species adapted to pre-event conditions. A recovery period longer than the entire history of Homo sapiens. That is what happens when the system crosses the threshold. And we are approaching that threshold at a rate the geological record says is comparable to the rate that triggered the crossing 56 million years ago. If the Silurian hypothesis is even partially correct, if some component of the PTM carbon signal was produced by an industrial process that we can no longer distinguish from natural causes at this temporal distance, then the PTM is not merely a climate event. It is a precedent, a record of what happens when a civilization on this planet overshoots its carbon budget. The event peaked, temperatures surged, extinctions occurred, and then, Slowly, over 200,000 years, the system recovered. Whatever produced that carbon signal did not survive to see the planet stabilize. There is no second chapter in their record, no recovery story, just a layer in the rock and an unresolved question. And here we are, writing the same layer with the same fingerprint at the same rate, with instruments precise enough to watch ourselves do it in real time. The question at the center of this parallel is not scientific, it is civilizational. We are the first species in Earth's history that can read the geological record of what happened before us and understand what it means for what we are doing now. The PTM data is available. The Silurian hypothesis has been published. The climate science is not ambiguous. The feedbacks are documented. The trajectories are modeled. The thresholds are theoretically understood, even if their exact locations remain uncertain. That is the difference. Whatever caused the PTM, whether it was a previous civilization or an entirely natural cascade, the entity that produced that carbon signal almost certainly did not have the ability to read a 56-million-year-old geological record and recognize its own reflection in it. We do. We can look at the PTM boundary layer in a sediment core and see, with molecular precision, what we are currently producing. We can measure our own carbon output, calculate its isotopic signature, project its trajectory, and compare it directly to the signal that preceded one of the worst extinction events in recent Earth history. And the comparison is not reassuring. The institutional response to this comparison is the same response we have encountered at every stage of this story. Careful acknowledgement, extensive study, a conspicuous absence of the most direct conclusion the data supports. Climate scientists know what the carbon curve looks like. They publish papers with carefully worded risk assessments. They present at conferences. They advise governments. And they watch as the emissions curve continues upward, year after year, decade after decade, through every agreement and every promised transition.